So we start from the theorem that we proved last time. So the statement is as follows. So if you start with a recurrent state and look at, say, I, you fix the recurrent state, and then you look at for every other state or for every state j, nu j is the expected number of visits to j between two consecutive visits to I, okay? Which can be also written this way, which is the expected number of visits to j in the first excursion to I. In that case, these nu j basically give an invariant measure of the Markov chain. If I is positive recurrent, then these nu j's are summable, and the sum is actually equal to the expected return time to the state I, which is finite because I is assumed to be positive recurrent. And then if you normalize each nu j by this sum, then you get pi j, which is a stationary distribution of the Markov chain. We proved this, although we did not talk about uniqueness. We just give, this is just an existential result. And we also saw in examples that stationary distribution existed, but it was not unique. In fact, we saw two examples where there are uncountably many stationary distributions. And in both the examples, it so happened that the Markov chains were not irreducible. Therefore, of course, the standard question that would come to your mind is, can we give a condition, sufficient condition, under which the stationary distribution will be unique? First of all, it has to exist, and then also it will be unique. So therefore, coming from those examples, coming from the experience of those examples, we can perhaps hope that if further the Markov chain is irreducible, then we can hope that stationary distribution would be unique. And that is indeed the case. So as stated in this theorem. So let me first state the theorem correctly. Suppose the Markov chain is irreducible and recurrent, and you fix a state I. Now, obviously, since this is irreducible and recurrent, it means all the states are recurrent. In fact, one state being recurrent is equivalent to all the states are recurrent because of irreducibility. So I is a recurrent state. So therefore, nu j defined as before gives an invariant measure for the Markov chain. So far, whatever I said has already been proved in the previous lecture. But now, furthermore, we can show that each nu j is actually a strictly positive and finite real number. Not only that, in this case, we can also show any invariant distribution is a scalar, any invariant measure, actually, it should be invariant measure, okay, is a scalar multiple of nu. If further I is positive recurrent, then the Markov chain has a unique stationary distribution. Okay, so this should be invariant measure. Okay, I'll make the correction. Slides. Okay, so let's try to, we won't completely prove this theorem. We'll give a sketch of the proof, and there'll be some parts which will be left out, and I'll ask you to read it from the book. Okay, so fix a state I, and then of course define nu j to be this expectation, which is the expected number of visits to j between consecutive visits to I. And since I is recurrent, this is already an invariant measure. First, we would like to show that for each j in S, nu j is finite. Now, an important component to this proof would be nu I is 1. Why is nu I 1? Because this is the expected number of visits to I in the first excursion to I, which is exactly 1. We start at I, And then first exertion ends before you come back to I. So therefore, you visit I exactly once in the first excursion. So therefore, this expectation is 1. This random variable is 1, and therefore the expectation is 1. We'll use this in the proof that each new j is finite. Also crucial would be the irreducibility. So since the chain is irreducible, we have that j leads to I, which means there exists a non-negative integer m such that Pajim is positive. So also note that since nu is an invariant measure, nu transpose p equal to nu transpose, which also implies that nu transpose Pm equals to nu transpose. So by repeated use of this equation, you can get that. Therefore, nu I, which is 1, basically sum of these properties, nu k, pkim, k runs over s. So this just follows from here, this equality here. Now this is obviously bigger than or equal to if you just put k equal to j, which is nu j times pjim, which basically gives that nu j is bounded by 1 over pjim. Note that pjim is positive. M is such that pjim is positive. Therefore, this is less than or equal to 1 over pjim, which is finite, obviously, for all j. So therefore, this is, we have actually shown, we are given a bound, and then this is obviously has to be finite for all j. Now note that this proof here, we use the fact that nu I was 1, but to be honest, nu I did not need to be 1. As long as nu I was something positive and finite, this proof would go through. In fact, nu I is 0 won't even matter in this particular proof. But as long as nu I is finite, this proof would go through. Okay? So therefore, in fact, it doesn't have to be I. Because of irreducibility, every state leads to every other state. So therefore, if you have one state, it doesn't have to be this specific state I. Okay? If you have any state, say L, such that nu of L is finite, this proof would go through.